Hello friends. In our last two sessions, we have discussed a single layer theory as proposed by Buzdik, two-layer theory as proposed by Burmeister. And I also told you the major limitations of these two theories. Next to that is three-layer theory. Now, in three-layer theory, what we assume that the flexible pavement is made of three layers. The top layer consists of all bituminous layers. The second layer, that is middle layer, consists of all unbound aggregate like base and sub-base layers, and the bottommost layer is of subgrade. So a flexible pavement is considered as made of three layers, and a load is applied at the surface having a pressure P here on a loaded area with a radius A. Now this is the first layer, layer 1, which is of bituminous material. This is layer 2 and this is layer 3. Each layer has certain value of E, that is E1, E2 and E3. And modulus of elasticity will decrease with the depth. The Poisson ratio mu1, mu2, mu3. And in this theory also, in three-layer theory also, mu1, mu2, mu3 are taken as 0.5. And let us say this is the thickness of the first layer, H1. This is the thickness of the second layer, H2. And this is subgrade. Now, when the load is applied at the surface, there are stresses, a vertical stress here, that is the interface of layer 1 and layer 2. Let us say this is sigma Z1, vertical stress here at the interface of layer 2 and layer 3, radial stress at the bottom of the first layer, let us say sigma R1, radial stress at the top of the second layer, that is, let us say sigma dash R1, and here it is sigma R2 and sigma R2 dash. These are the stresses. And similarly, you have strain at the interface of layer 1 and layer 2, and strain at the interface of layer 2 and layer 3. Now the vertical strain, epsilon z, and this is a general equation of strain, and this is equal to 1 upon E into sigma z minus mu times sigma r plus sigma t. Now this sigma t is tangential stress, sigma r is radial stress, sigma z is vertical stress, and mu is the Poisson ratio. So if you consider a homogeneous material or continuity in the interface, then sigma r will be equal to sigma t and this mu will be equal to 0.5, and therefore this equation can be written as sigma z minus sigma r, twice of sigma r multiplied by 0.5, that is your vertical strain. If you are considering vertical strain here, then consider E1. If you are considering here, consider E2. And accordingly, it will be sigma Z1 minus sigma R1 or sigma Z2 minus sigma R2. Similarly, now radial strain epsilon r is equal to 1 upon E into sigma r minus mu times sigma t plus sigma z. That is the equation for radial strain. And again, if you consider mu as 0.5, sigma t is equal to sigma r, then this equation will be equal to 1 upon 2e into sigma r minus sigma z. Compare these two equations. Epsilon z is twice of epsilon r. Radial strain is half of vertical strain and in opposite sign. So now this you can understand by the definition of mu also, because when you take mu is equal to 0.5, the radial strain is half of the vertical strain. That is how this is coming here. Sigma epsilon z is equal to minus twice of epsilon r. Now the question is, how do we calculate sigma z, sigma r? Sigma r1 dash or sigma r2 dash. Jones in 1962 found that the stress, vertical stress and radial stress in a three-layer system or multi-layer system depends upon 4 parameters. And these parameters are K1, K2, A and H. Now K1 is E1 upon E2, K2 is E2 upon E3, A is A upon H2 and H is H1 upon H2. And based on these 4 parameters, Jones in 1962 produced tables to find out the stress, radial stress and vertical stress at the interface of 2 layers. Now this table looks like this, that you have the value of H, then value of K2, value of A varies from 0.1 to 3.2, H can vary from 0.125 to 4, and similarly this K2 can be 220 or maybe 200 also, and similarly K1 can also be either 2, either 20 or 200. Based on these ratios, 4 ratios, you can read the value of ZZ1, ZZ2, ZZ1 minus RR1 and ZZ2 minus RR2. Then sigma Z1 is P into ZZ1. And similarly, sigma Z2 is P into ZZ2. Sigma Z1 minus sigma R1 is equal to P times ZZ1 minus RR1. And similarly, sigma Z2 minus sigma R2 is P is the pressure at the surface, ZZ2 minus RR2. And if you want to find out the radial strain at the top of the second layer or third layer, that is sigma R1 dash, then sigma Z1 minus sigma R1 dash is equal to sigma Z1 minus sigma R1 divided by K1. And similarly, sigma Z2 minus sigma R2 dash is sigma Z2 minus sigma R2 upon K2. Using these equations, you can find out the radial stress at the interface. And epsilon z, vertical strain or horizontal strain, I told you the equations that depend upon the value of sigma z and sigma r. Let me take one example here now. Let us say you have a 3-layer system. The first layer thickness is H1, that is 300 millimeter. Second layer is of base and subbase. H2 is 150 millimeter, and third is subgrade. The modulus of velocity of these layers, E1 is 2000 MPa, E2 is 100 MPa, and E3 is 50 MPa. The tire pressure is 0.5 MPa on a circular area with radius is 120 millimeter. Let us take this example. So let us calculate what is K1. K1 is E1 upon E2, that is your 20 now. K2 is E2 upon E3, 2. Capital A is A upon H2. A is 120, 120 by 150, that is 120 by 150.8. And capital H is H1 upon H2, that is 300 upon 152. Small p, that is your pressure, is 0.5 MPa, that is given in the question. Find out what is the vertical and radial stresses and strain in the pavement at this point and at this point. Now you enter the table with these values of 4 parameters: K1 20, K2 2, A 0.8 and capital H 2, and find out what is the value of ZZ1, RR1, ZZ1 minus RR1 and ZZ2 minus RR2. So these are the values of interest, right? So sigma Z1 will be P into ZZ1, and this is 0.5 multiplied by ZZ1 is 0.03412, that is 0.0706 MPa. And similarly, sigma Z2 will be 0.5 into ZZ2. ZZ2 is 0.02023. So this is equal to 0.010115 MPa. Now sigma Z1 minus sigma R1 is P times ZZ1 minus RR1, and this value is 0.68382 multiplied by 0.5. So this value is 0.34191 MPa. Now you know sigma Z1 here, so we can calculate what is sigma R2. So in this equation, if you put value of sigma Z1, sigma R1, you can find out that will be minus 0.3248 MPa. Now minus sign here indicates that the tensile stress. And similarly, you can find out sigma R2, that is again sigma Z2 minus sigma R2 is equal to P times ZZ2 minus RR2. ZZ2 minus RR2 is 0.03093, and again if you put value of sigma Z2 from here, you can find out what is sigma R2. So sigma R2 is equal to minus 0.00535 MPa. So now you have this sigma Z here, sigma Z1 here, sigma Z2 here, sigma R1 here, sigma R2 here. Now the question is, what is the stress here? Sigma R1 dash, and here sigma R2 dash. Now this can be found out using this equation, that sigma Z1 minus sigma R1 dash is equal to sigma Z1 minus sigma R1 upon K1. Sigma Z1, sigma R1 you know, that is your 0.34191 MPa divided by K1. K1 is 20. So this will be 0.34191 divided by 20, whatever it is, 0.007, and sigma R1 dash now is sigma Z1 minus this value 0.017096, and therefore if you put sigma Z1 is equal to 0.0106, it will be minus 0.000035 MPa. This is sigma R1 dash. And similarly, you can find out what is sigma Z2 minus sigma R2 dash is sigma Z2 minus sigma R2 upon K2. You know sigma Z1, sigma Z2, you can find out what is sigma R2 dash. So sigma R2 dash will be equal to 0.00238 MPa. This is positive and therefore this is compressive. Now you can find out the strain value also. The first strain sigma Z1 is 1 upon E1 into sigma Z minus sigma R. Sigma Z1 minus sigma R1. Now sigma Z1 minus sigma R1 you calculated here 0.34198. E1 is 2000 MPa and therefore this value will be 1 upon 2000 into 0.34191, or you can say that this value is 0.00017095, and this is positive and therefore this is compressive strain. Similarly, sigma Z2, epsilon Z2 at this interface will be equal to 1 upon E2 into sigma Z2 minus sigma R2. Now here also you know sigma Z2 minus sigma R2, this value 0.5 into 0.03093. E2 you know that is 100, and therefore this value also you can find out, and this epsilon Z2 will be equal to 0.000154, and it's also compressive strain. So you can say 154 micron. Now once you know sigma Z, epsilon Z1, epsilon Z2, if you want to find out radial strains, those can also be found out, because I told you that the radial strain is half of the vertical strain, and therefore epsilon R1 will be minus half of epsilon Z1. This is equal to half of this value, minus half of 0.00017095. And similarly, epsilon R2, radial strain at interface 2, will be half of this value, but in opposite direction. That is, this will be in tensile strain. Tensile strain, this is compressive strain, vertical. That is how you can calculate stress and strain at different interfaces of a 3-layer system using Jones table. But one thing you should note here, that in this example we have taken values of E1, E2, E3, H1, H2 in such a manner that these 4 ratios K1, K2, capital A and capital H, they are exactly same as what is given in the table. Now if the value of E1 is changed, let us say instead of 2000 take 2500, then E1 upon E2 or K1 will not be the same as in the table, and in that case you need to interpolate the values, and to interpolate a single value you need 3 points. So your efforts increases by 3 times, and if all the 4 values are outside the value which are given in the table, then the efforts required will be 3 into 3 into 3 into 3, that is 81 times. To resolve this problem, PT in 1962 converted Jones table into charts so that interpolation is easier. You don't have to make many calculations, and these charts look like this. They have all these variables A, H, K1 and K2. This is just one example of the chart where you have different values of K1, K2 and A and H, and you can get on the y-axis RR1 minus ZZ1 upon 2. And using these charts, you can find out the same values of stress and strain as we have done in case of using the values given in Jones table. Now, with the availability of high computing machines, it is possible to write the computer programs, and therefore softwares are available now to calculate all these stresses and strains in a multi-layer system, and CANlayer is one of them. So in the next session, we will discuss how CANlayer be used to calculate the stress strain in a multi-layer system. So friends, thank you very much for watching this video. If you have any question, you can write in the comment box.